Hello everyone, here we'll be discussing functions of several variables. It's a pretty straightforward concept actually. It's just usually what we're kind of used to from functions of one variable, f of x. Then we'll have functions of multiple variables, for example, f of x comma y, where you plug in two values and one value gets outputted. So let's take a look and let's recall that the graph of a function f of x on the xy plane, so in other words in two dimensions, is the set of ordered pairs x comma f of x. And normally we consider y equal f of x, so this is, I think, pretty intuitive for us because y is equal to f of x in this case, where x is in the set D, where D is the domain of the function f of x. Okay, so that makes sense. It's just a set of all points that are of the form x comma y, or y is equal to f of x, and you can only plug in x values that are in the domain of f, so that makes sense. But now we say that a function of, let's say, two variables, f of x comma y, is such that its output is a real number, making its graph in R3, so in three dimensions, the set of ordered triples x comma y comma z. You'd expect this to be z, where z here is f of x comma y. So something I want to say here is that usually we want y to be f of x, here we want z, the third variable, to be f of x comma y. So I think that is a pretty intuitive statement, so that we have an intuition as far as what the graph kind of looks like. And by the way, opposed to what we've seen for vector functions actually have graphs that are these space curves that are kind of one-dimensional in some sense. They're kind of imagine like lines, but they may be curvy, but they're one-dimensional. They don't have an actual surface. Here, the graphs of a two-variable function in 3 space is actually going to be a surface. And we'll take a look at a few examples. They're going to be a little hard to graph, but I have a way of kind of showing you that. But in any event, let's continue. So, so where x comma y, this ordered pair that is the input of f, so it's almost like there's two inputs actually, is in the set D, where D is the domain of this function f of x comma y. Which sounds a little funny, but we'll talk more about that with this example. So in this example, we not only want to evaluate the function for this input, 3, 2, but we also want to sketch the domain of the functions. So why we're sketching the domain is because the domain, unlike what we saw for functions with a one input, there the domain will normally be an interval, which is, you think of like a one-dimensional shading of the real number line, whereas here the domain will be a shading of a two-dimensional region, which kind of makes sense. Kind of like graphing in 2 dimensions, the domain is in 1 dimension less. Graphing in 3 dimensions, the domain is a shading in 1 dimension less. So that part I think is pretty intuitive, but the idea is just a little new. So let's just get right into it. So if we want to plug in 3, 2, then f of 3, 2 in this case is going to be, well, let's see, that's the square root of 3 plus 2 is 5, and plus 1 is 6. That's radical 6 on top, over x minus 1, x is 3 here, so that's going to be over 2. And I'm going to leave it like that. Radical 6 over 2. That can't really be simplified, so that's fine. And now, how does the domain look? Well, there's a few things going on here. Not only do we have a denominator, we also have an inside of a radical. So let's recall that for denominators, we cannot have the denominator be equal to 0, and for an inside of the radical, we cannot have the inside of the radical be less than 0. So in other words, the inside of the radical must be bigger than or equal to 0. So we'll do our best to describe each of these. I think we'll be okay, but let's see. For the inside of the radical part, if you solve for y, you'll have y is bigger than or equal to negative x minus 1. But for the denominator, we must have it so that x is not equal to 1 if you add 1 to the other side. So I may need to investigate further here to actually shade, or I guess sketch this domain. But this looks like a line if it was equal to, but y is bigger than or equal to this is a shading on one side of the line, and then we have to exclude the line, vertical line x equals 1. So after we finish talking about 2 as far as evaluating and discussing the domain a bit, then we'll actually sketch after the fact. So let's get into part 2 now. So let's evaluate this at 3, 2 if we can. And let's plug in x to be 3, y to be 2, so it's 2 squared minus 3. Notice 2 squared minus 3 is 4 minus 3, which is 1. So this in actuality is 3 ln of 1. ln of 1 is 0, so that makes this whole thing 0. So it does exist, actually. It wouldn't exist if the inside was negative. And in fact, that leads me to my next idea here. Similarly, how we found the domain of this, which was the set of these two, here, for the domain of this function, multiplying by x is fine for any value of x, but ln only exists when the inside is positive. So the inside must be bigger than 0. So if we actually solve that inequality, let's see if we can do it. We get y squared minus x is bigger than 0, but if you add x to the other side, we get y squared is bigger than x. Which, if this was equality, this reminds me of the sideways parabola y squared equals x. But since it's not equality, it's kind of like this dotted parabola. Well, again, we'll have to actually discuss what that looks like as far as the sketching of the domain goes, which I don't think is too big of a deal, but it definitely is not a bad idea to discuss these things. So I'm going to erase all of this, and now we'll move on to actually sketching these domains now. All right, so this is where we left off. We wanted to find the sketching of these domains, and what we ended up finding out is here for the first one, if the denominator is not 0, we get this inequality, and if the inside is bigger than or equal to 0, we get this inequality of this radical in the numerator. So now I'm going to try to graph each of these individually, kind of, but all on the same xy plane. Now again, if this was equality, we'd have the line y is equal to negative x plus 1. Actually, I wrote this wrong. It would actually be minus 1, because notice, just write this here like I did. So we want this to be bigger than or equal to 0, so if you subtract x and 1, then you get negative x and negative 1 on the right side. And similarly here, this is not equal to 0, so you add 1, you get that. Okay, so now that that's sorted out, let's see if we can make a little bit of progress. And I want to graph the line if it was equality. So if it was equality, we'd have a y-intercept of negative 1 and a slope of negative 1 over 1. So kind of think of slope-intercept form. So we get something like this. Let me try to draw that a little cleaner. Something like that. Now, since it's or equal to, this line remains solid. Since it's bigger than, we're shading above. Basically, every point above this line or on the line will satisfy this inequality. I'm not going to go over the details of that, but you can actually convince yourself that is indeed the case. If this was equality, we'd have the line x equals 1, which is this vertical line right here. Since it's not equality, we have the dotted vertical line of x equals 1. If it was equal to, then we'd actually have a solid line. So this dotted line is actually x not equal to 1. And in fact, x not equals 1 really is a shading of everything in the entire xy plane except for this line itself, which is kind of a weird thing to think about. But anyways, what we want to do is we want to shade above this line, and we do not want to include this vertical line here. So what that basically looks like is the following. So I'll try to shade this kind of quickly. So we kind of had the split in the middle. So no point on this vertical line is actually valid when plugging it in. So for example, this point here, 1, 0, can't be plugged in. And it makes sense because when you plug in 1, 0, right away the denominator is going to be 0, so it's not valid. And in fact, any point on this line will have an x value equal to 1, so it'll give you a 0 denominator. Anything that's below this line here, let's say like this guy, 0, negative 2, will give you an inside of the radical that's negative. So if you plug in 0, negative 2, x is 0, y is negative 2, you'll get 0 minus 2 plus 1, which is negative 1. That's a negative 1 inside the radical, and that doesn't exist. So that's a reason why that's true. Now, this is equivalent to what we have seen in 1 dimension, or I guess in 2-dimension graphing, with an interval. So imagine shading an interval. This is kind of like our interval. So kind of imagine what we have for graphing on the xy plane. If you have a graph like something like this, let's say, then the domain is the projection onto the x-axis. Except for this point, because there seems to be a vertical asymptote here. So we'll have something very similar in 3 dimensions, meaning here how this is our floor, the x-axis is our floor here, and the domain is the shading of all possible x values. Here, the xy plane is kind of like our floor, where the shading represents all possible xy values that can be plugged into the function. So when you actually go about graphing this thing, if this is x, this is y, and this is z, you want to have this shading here, and it's going to be really hard for me to draw that, but it would basically look kind of like something like, let me see if I get it right. So the y-axis is going to be, so it would be something like this, or we're shading all of this. So this is kind of like our floor. So whatever your curve would look like of this if you were to graph this in 3 dimensions would only exist on top of this floor. Anything that's on top of this, because remember the xy plane is treated as our floor in this case, anything that's on top of this will be non-existent for this graph. So I hope that kind of makes sense. And now it's a little hard to talk about because it's in 3 dimensions, but again, I'll try to show you a way of graphing this later on in the video. Now for this one, this is a little interesting. Actually a little more straightforward. The graph of y squared equals x is the sideways parabola, this. So this is actually the graph of y squared equals x. Since this is y squared is bigger than x, then we want to shade everything that is above the parabola, which is kind of hard to describe. But I guess we can pick a test point. So for example, what if we pick this point inside the parabola? So it's either inside or outside the parabola. But let's say we pick this point, which is 1, 0. If you plug in x equals 1 and y equals 0, this doesn't actually work, because you'll get 0 is bigger than 1, which is not the case. So that means you don't shade anything inside the parabola, but instead you shade everything outside of the parabola. And beyond this, since it's not or equal to, this is actually a dotted parabola. In other words, we cannot plug in points that are on the parabola itself. So now to shade everything else that is not inside the parabola, so everything outside of the parabola, we could do something like this. So if you were to graph in 3 dimensions, your floor would only have this part shaded, so you can kind of imagine what it would look like and what your surface would be. As far as what the surface looks like is not very obvious, but we can definitely see that extending into the 3rd z dimension, there would no be surface over this blank region, non-shaded region. So again, I hope I'm describing things okay. I think it should make sense. So now we'll move on to the next idea. Right, so now I want to get a better idea as far as how we sketch graphs in 3 dimensions. I said I would show you a few. And really to get the best idea is to consider what are called level curves. Before we get there though, I want to try my best to graph some things we've kind of seen a little bit of already. So let's sketch the graphs of, well, these 2 examples here. So f of xy equals 6 minus 3x minus 2y, and then f of xy equals the square root of 9 minus x squared minus y squared. Now remember that we're always letting f of xy be equal to z. So notice what we have here actually is a plane, because you can move everything to one side so that we have 3x plus 2y plus z is equal to 6. And this is what we're very often reminded of when it comes to an equation of a plane. So this is actually a plane. Aha. And since it's a plane, we can just find the intercepts by plugging in 0 for 2 at a time. So let's try our best to graph this on 1-3 space. And let's see if we can get an idea. So if x and y are equal to 0, then z is 6. So that's right here, let's say. And if y and z are equal to 0, then 3x is 6, so dividing by 3x is 2. So that's a little closer. So imagine just for scaling, that's 6. And then a third of that would be 2. So around here, that's x equals 2, let's say. And if you want y, by setting x and z equal to 0, you get 2y is equal to 6 divided by 2. Y is equal to 3, which is about halfway. So let's say that's 3. Perfect. So now connecting these, we get this triangular piece, which is just a section of the plane. So now I'm going to shade this, but just know that the way it's tilted gives us an idea of how the actual plane is in 3 dimensions, which again is a shading beyond this, so extending indefinitely in each direction. So this is just a triangular portion of the entire plane that's tilted like that. So we can kind of imagine how it looks in 3-dimensional space. This one will actually tackle in a very similar way, but the shape will be completely different. So let's take a look. So here we let f of xy equals z. Let's do the same thing here. Now, so far it doesn't look like we can go anywhere, but the thing that I think gets in our way is the radical. So to get rid of the radical, let's square both sides of this equation, and then we'll actually make a lot of progress. Notice when you square the square root, they cancel out. And that allows us to get the following. Z squared is equal to 9 minus x squared minus y squared. If you add the x squared and y squared to the other side, kind of like we did here, then we get x squared plus y squared plus z squared is equal to 9, which is 3 squared. Now, if you don't remember, we actually saw an equation of a sphere, which was x minus h squared plus y minus k squared plus z minus, I think it was L squared equals R squared. And that was a sphere with center H, K, L with radius R. So in this case, the center is going to be 0, 0, 0 because x minus 0, y minus 0, z minus 0 technically. And the radius is going to be 3. So if we were to graph this in 3 dimensions, we need to go out in a 3, distance of 3 in each direction. And we connect to get a sphere. The only thing is that technically, since it's a positive radical, it's not a plus or minus, we technically only have the upper part of the sphere. Kind of like you would see in 2 dimensions when you have y equals the square root of 9 minus x squared. So imagine that y squared part not being there. That would represent the upper half circle, not the full circle. Basically, z is only positive. Since z is only equal to positive values for the original function, then we only consider positive portions of the sphere. So I'm going to try my best to draw this. It's going to look a little funny though. So here we have kind of the circle piece up here, and then we have this like that. So I'll try my best to draw this again. It may look a little weird. In fact, the more I think about it, it's just going to look really, really funny. But this is like a circle, and then we have this part here. Maybe it looks a little better. So it's kind of like this dome shape. And it's the surface of this. So maybe this is a better shading of that. The upper half sphere with radius 3, center at the origin 0, 0, 0. So I think that's okay. All right. So now for level curves. So here I say the level curves of a function f of x, y are the curves f of x, y equals k. So we're basically letting z be equal to a constant, and then we're kind of considering what the curve of x and y would look like. So I'll describe that in a moment. And of course, we want k to be in the range of f of x, y, or else it wouldn't make sense. So you want to make sure k is something that's valid. So like here, for instance, f of x, y can't be equal to a negative number because it's not in the domain of this function. So I hope that part's okay. And in fact, speaking of that example, we want to find, in this example, want to sketch the level curves of this function for k equals certain values. Now, just to get a kind of general idea what level curves kind of look like, imagine we have some surface in 3 dimensions. I'll try to draw some surface. So we have something like this in 3 dimensions. The level curves basically correspond to these kind of curves you would get at each particular level. And in fact, very often if you look at maps, you'll kind of see something like this. If there are maps with level curves, that describes how high certain things are. So seen from above, here you'd have the xy plane, and then the curves would look something like this. So you may have something like that for k equals a certain value, and then for a different k value, you may have something else. So this, for all we know, this black portion here is k equals 32, which implies that it's way higher than this black curve. So it gives us an idea as far as depth goes, where these k values really represent in the z dimension. So it's a way of describing kind of this idea here. So let's see if we do it with this one. So we're going to set this equal to 0, 1, 2, and 3. What I want to do is I kind of want to use this fact here to make it a little better. And I want to solve for, and in fact, let's use this one here. So notice that all I would do would be letting this equal to z, squaring both sides, moving things around so we get this. And the other thing I want to do is I want to subtract z squared to the other side. So here z squared is going to be 0 squared, 1 squared, 2 squared, and 3 squared. So essentially we're going to be looking at the graph x squared plus y squared is equal to 9 minus k squared. So I hope you agree with what I'm saying here. If z is replaced with k and we subtract it to the other side from this equation, we get this equation. And then when k is equal to 0, 1, 2, or 3, we basically get circles because x squared plus y squared is a circle in the xy plane of the given radius being the square root of this. So when k is equal to 0, we get the circle of radius 3. So this is when k is equal to 0. When k is equal to 1, for instance, then this becomes 8, which would be a circle of square root 8, of radius square root 8. Square root of 8 is a little less than 3, so that's going to be something like this. Try to draw it in a different color maybe. Don't have too many colors, so it's going to get a little weird, but that's okay. So the red is k equals 1. Then when k is equal to 2, we'll have 9 minus 2 squared, which is 9 minus 4, which is 5. So that is a circle of radius square root of 5, which is about 2 point something. So let me use green for that. So that'll look something like this. And for the green, that's when k is equal to 2. And then k is equal to 3, well, you'll start to see actually what happens here, which is kind of nice. Because when k is equal to 3, you have 3 squared, which is 9. 9 minus 9 is 0. So in fact, we really just have this point, which I'm drawing in red, which corresponds to when k is equal to 3. So really what we have are these kind of heights. And they correspond exactly to these level curves here. When k is equal to 0, we basically have the floor of this half sphere. When k is equal to 1, we basically have this kind of belt here, which goes around like that. When k is equal to 2, we get a little higher out here. And finally, when k is equal to 3, we don't have any circle, it's just a point. So that actually represents the vertex, if you will, or the highest point of the sphere. So I hope that part kind of made sense as far as these level curves are concerned. I feel we should do maybe one more example of level curves, and then finally we'll focus on the last thing I want to talk about in this section, which is when we consider functions of more than 2 variables. Right, so for this example here, we want to sketch the graph of this function h of xy equals 4x squared plus y squared plus 1. We want to do it in a very similar way to the previous problems, considering level curves. So we're going to let this be z. In fact, we want it to be k eventually. And notice actually that if you let this be equal to k, we end up getting a curve only in x and y. So we can actually subtract 1 to the other side. And if we imagine that z is equal to k in the context of level curves, we actually get the following. Let me kind of rearrange things. We get 4x squared plus y squared is equal to k minus 1. If you actually divide both sides, it's not very obvious, but if you divide both sides by k minus 1 and write it in a very particular way, you get x squared over 1/4 k minus 1 plus y squared over k minus 1 equals 1. And if you've ever looked at a section in conic sections, you'll actually recognize this as being an ellipse. Of course, when k is equal to 0, you get negative values, and that kind of contradicts this equation a bit. But when k is greater than 1, we actually get these ellipses. And it looks like the y value is always going to be larger because the denominator is always going to be larger than this denominator. So what that tells me is that the ellipse will actually be elongated on the y-axis. So I'm actually not going to, I'll spare you the details a bit, but let me just say that the lowest we can be is when k is equal to 1. In fact, when k is equal to 1, you get 0 denominator, so it doesn't even really make sense. But I won't tell you what the lowest k value is, but at least we'll kind of consider some k values. So let me just kind of show you a little bit what's going on here. So if we were to let k equal, I want to pick like a value that works out nicely. But it's hard to tell because you want it to be like a square in order to get a nice, again, I'll spare you the details. But you end up getting something that looks like this. So this is an elongated ellipse. Well, ellipse is an elongated circle, but it's in the y direction, stretched out in the y direction, so it's a vertical ellipse for a specific k value. Now, it is unclear at this moment that if you increase the value of k, do you get a ellipse that is outside of this or that is contained inside of this? Now, I'm not picking a particular value, but maybe we should. Let's plug in k equals 2. So when k equals 2, we get an ellipse like this. In fact, let's see exactly what we get. So when k is equal to 2, that becomes 1, so we get x squared over 1/4 plus y squared over 1 equals 1. The next value I want to plug in is something where k minus 1 is a square, so how about like 5 works? Because when k is equal to 5, then you get, oh look at that, you get 1 here and you get 4 here. Because 5 minus 1 is 4, so that's, yeah, that works out. So we actually end up getting x squared over 1 plus y squared over 4. So here, for k is equal to 2, the x value has to be the square root of 1/4, which is 1/2. What I'm discussing really has to do with conic sections and ellipses. If you haven't seen it before, it's okay. But that's basically what we're looking at. And when k is equal to, let me use a different color here. So let's use red for k equals 2, and let's use green for k equals 5. So when k is equal to 5, the y value now is the square root of 4, which is 2, which is way up here, let's imagine. And the x value would be 1, which is the square root of 1. So we actually get a larger ellipse. And remember that k's correspond to z values. So essentially what's happening is you get these ellipses that get bigger and bigger and bigger as k gets larger and larger and larger. Meaning as z increases towards infinity, we get these rings or levels getting wider and wider. And the image we actually get is the following, believe it or not. We get this shape that is known as a paraboloid, and in this case it's an elliptical paraboloid that's elongated in the y direction. And you can kind of see that I'm trying to draw these levels that correspond to these elliptical rings that get wider and wider and wider as z gets larger and larger and larger. So again, this is pretty hard to visualize, and I'll do my best to actually show you a three-dimensional graph after we finish. Now the next and last thing we need to discuss here are functions of more than two variables. And here I say f, this is a very general statement, f of x1, x2, x3, all the way to xn is a function of n variables, where the so-called n tuple, x1, x2, x3, all the way to xn, is in n space. So it's an Rn, you would say. So an n-dimensional space, which is really, really, really hard to imagine graphing. So, yeah. So in this example, we want to find the domain of this three-dimensional function, or function of three variables, f of x, y, z. So this, you can call this guy w, normally how you call f of x, y, or in this case, h of x, y, z, you would call this fourth variable w. And the graph of this would be some four-dimensional object, which is really hard to describe. So I'm not going to get into that, but we will discuss the domain. The domain actually is really easy to talk about because x and y are multiplied here, so they can be anything. The domain of sine can be anything as well, so z can be anything here. So in other words, this term actually doesn't really matter. This term is actually a-okay. It doesn't give us any restrictions on x and y, or z. Here though, we saw this earlier, the inside of ln must be bigger than 0. So what we can do is we can actually solve the inequality, z minus y is bigger than 0, and then we can actually add y to the other side. If this was equality, then this would be the line z equals y. And in fact, that's a line on the zy axis. So I'm going to try my best to draw this. It's going to look a little weird. But on the zy axis, we have this line that goes like this. So if you imagine the zy axis only. And in fact, I think I may have even done that part wrong. Yeah, it's more like this actually. But in three-dimensional space, it's actually a plane. Notice. So in reality, we have this kind of plane that's tilted like this that passes through the origin of three-dimensional space. And moreover, when z is bigger than y, we actually have above this plane. So it's the shading of this three-dimensional space above this plane. So in fact, you can say the domain D is the set of all x, y, z order triples such that z is bigger than y. And in fact, this is known as half space, you can say. So kind of like if you were to shade the left of the XY plane, or I guess, I'm gonna do this in green, I guess, but imagine this shading, I did that kind of bad. There we go, this shading of the XY plane, this would be the half plane, because it's half of the plane. Here, this is cutting space in half, so this is known as a half space, which is kind of interesting, but this is actually the answer here. That's the domain, and this is somewhat of a shading of the domain, where you're shading every point in three-dimensional space above that plane, which looks like this crazy mess. It's really hard to describe and draw on the board especially. And notice, that's just the domain. We haven't even described how to graph this thing, and I don't even want to do that because graphing this would be in 4 dimensions, which is really hard to describe. So now I'll give you some visualization using a graphing utility, and it's going to be quite nice. We'll see this and a few others that we saw in this section. All right, so I wanted to show you all this app called Quick Graph. I have a iOS device, so if you actually go to the App Store and look up Quick Graph, it's the first option, it's free, it's in green. And I've actually added these graphs already. I want to take a look at a few of them. So let's first consider this graph y is equal to x squared, which we know just is a parabola. But notice that since this equation y equals x squared is independent of z, actually this extends in the z direction and we get this parabola, but it's like this sheet. So it's this plane that actually extends indefinitely in the z direction, which is nice. And if you double tap here, you actually get different ways to describe this. So either that shading completely, or you get kind of this wire grid like this. And it gets a little hard to rotate because it ends up kind of wobbling, so that'll happen. Anyways, let's take a look at the next thing I want to show you, which was this one we saw where we actually found the domain of this thing. Let me kind of make it like this. And if you don't recall, the domain of this was the shading of the xy plane except for this sideways parabola, y squared equals x. And in fact, this is exactly what you get. It looks a little funny, just the way the program is trying to graph it. But if you just imagine looking at this black region here, that looks kind of like, I don't know, it looks a little hard to describe, but it's basically this parabola. And everything that is shaded is that. So it's kind of interesting. And it kind of seems that there's stuff missing over here, but I think that has to do with the range. It definitely has to do with the range, because if you look at the XY, if you look at the XY plane part of it here, then actually all of the XY plane is shaded except for that region there. It looks like more is unshaded, but that's just the program not able to process too much at a time. If we look at the next thing, which is this plane, we got a really nice image here. It's just this flat sheet. You want to see it like this wire mesh view. That's nice. And we actually graphed the triangular region, and you can kind of see a little bit of what that looks like. So this program is definitely really nice if you want to get a really good idea as far as what surfaces in 3 dimensions look like. You can play around with it. The last thing I want to talk about was this so-called elliptical paraboloid. And it looks really, really trippy. Yeah, that's what we end up getting. And this is the solid version. If we kind of zoom in, it starts to smooth out a little bit. There we go. But you can kind of see it's, let me do the wired mesh version. You can definitely see that it is indeed elliptical. It's still a little hard to kind of view. You have to zoom out quite a bit to see it. But now we're inside of it, yeah. Anyways, that concludes the video. I hope you all really enjoyed this. I think this is a really nice way to end things, to get a nice visualization via an app. And it's something you can all play around with, I hope. So I'll see you in the next video. We'll discuss more. In fact, we'll actually get into limits involving functions of several variables. And that's going to be a lot of fun, really interesting stuff. So I'll see you in the video for that. Thanks for watching. Hope you enjoyed, and I'll see you then.